Alright, gang, here we go. This is for Physics, Unit 9, Part 4. We're going to be talking about current. Should be a nice short video. We're going to divide Part 4 here into 3 parts. One about current, one about resistance, one about power. Alright, each one's going to have its own little things that you need to keep track of and its own little simple formula. Individually, they're not too hard, but put them all together and it get kind of confusing. Alright, so electric current. Now, electric current, this is essentially like the charges that are moving through your wires or whatever it is that's conducting your electricity. Okay, and so it's defined as the rate at which charges flow through an area. Now, when we're talking about current or about electrical flow or electron flow or anything like that, what I find to be a good analogy is to think about how water travels through pipes. If water, if you can kind of keep that in mind, water and electricity as they travel through pipe have a lot of similar characteristic. Electrons, as they flow through a wire, they're going to fall from a high potential energy to a low potential energy, just like water going through a pipe. But water won't ever run uphill; it'll always go downhill where it has lower potential energy. Same thing with electrons. And as we move forward in our ideas of electric flow and current, so on and so forth, that you'll notice that there's a lot of cases where we'll relate back to this analogy. Now, there's a couple of important cases where the analogy kind of falls apart, and but for the most part, this analogy works pretty well. All right, so electric current. So just imagine, these electrons are flowing through this pipe, and we've got this little lighter shade area here, and that's the part we're counting. So we're just saying, well, how many coulombs are passing through this area per second, or coulombs per second? And you'll also see these rated as amps, or the unit, the SI unit for current is amps or amperes. All right, if you hear about amperage and stuff like that. And 1 amp is also equal to 6.25 times 10 to the 18th electrons per second. So, but essentially all they did here was just convert coulombs to electrons using the charge of an electron. Remember, the charge of an electron is 1.602 times 10 to the minus 19th coulombs. All right, is the charge of an electron. 1 electron. All right, so here we've got the formula for electric current. Our current is equal to our change in our charge over the change in time. It's essentially just it's a rate of change, right? Like velocity or anything else. So it's the charge passing through an area in a given amount of time. Okay, now, so that's pretty easy, but now we got to talk about what's called conventional current. All right, so current can be defined, remember, look at this, it was defined as any charge flowing through an area. Now here specifically in the picture we've used, it's negative charge. So you can imagine these electrons, but charges can be positive or negative. And so what occurs is when we talk about current, all currents have the same properties. And so what we do is we just define what we talk about is conventional current. And conventional current is defined as the flow of positive charge. Okay, and so here we've got negative charges that are moving, but when we talk about current, we'll always be talking about conventional current, so it would be the equal amount of positive charge moving in the opposite direction. All right, so this would be where our eye is headed and be in the equal amount of charge, but it's headed in the opposite direction. All right, so what this amounts to is, since we're going to be primarily focusing on electricity in our class, okay, really what this amounts to is that our current, okay, is always opposite of the way the electrons are actually flowing, okay? And there's a couple other different examples of current, right? We've got this guy, so if we could make like 3 different things here. And so we've got, our electrons, if our electrons are flowing this way, then our conventional current would be an equal amount of charge flowing this way, right? But you could also have, like in an electron, or not an electron collider, but a particle collider. Essentially, these are hydrogen atoms, helium and hydrogen atoms, that they send through, speed them up using magnetic fields, electric fields, so on and so forth, get them super fast, and then run them into each other. But those are the flow of positive charges. So for the particle colliders, our conventional current is the same. So we got a positive charge going this way, positive charge going this way. But then in stuff like chemical reactions, especially redox reactions, all right, you have a flow of both ions, and this happens in gases and stuff like that. So you'll have positives that are going this way, but at the same time, you'll have electrons that are going this way. Oops, those really should be the same size arrow, but we do what we can here on PowerPoint. And then, so really, what this would be represented as is 2 positive charges an equal amount of total, like, magnitude of charge, and they'd both be flowing in the same direction as the positive. Okay, and so these are the different ways we can keep track of and convert whatever charge movement is going on in our given situation into conventional current. This guy here happens to be like what we're going to focus on. So essentially what you need to keep track of, boil it down to the nuts and bolts here, is the fact that these electron flows, our current is opposite of that. All right. Now, another interesting idea is thinking about the velocity of these electrons through the walls, or through the wires, excuse me, and through the walls. The wires are in the walls, right? And so, so if you're thinking about velocity of these electrons, you like walk up to your light switch and you hit the light switch and you go, oh, the light turned on almost immediately, so the light must be going, the electrons must be going really, really fast. So you might be tempted, reading this question, it says, which speed below do you believe most closely approximates that of the electrons? You might be looking at these and you say, well, the speed of light, that's probably pretty accurate. I mean, electrons are moving really fast. That light turns on almost immediately. This one's also pretty dang fast, but this one's really slow. Now, what actually happens is this one is the closer approximation to the velocity of those electrons. Okay, and what it really amounts to is that if you can imagine having like a row of marbles, okay, and these row of marbles, oops, these should all be touching one another for my analogy. So these row of marbles represent our electrons, and so you imagine if these marbles were all shoved in like a little tube where they can't go anywhere, or like just rolling on, somewhere that they can't like roll side to side, just left and right, and you shove another marble right here. Well, this marble from here to here is not going to move very much, but as a whole, these electrons are all going to move the entire distance, however far it goes. And the wires are the exact same. In the wires in your where you're having electric flow, you've got these electrons, and they're all crammed in there, and they're neutrally charged, whatever. And you flip the switch, and now these electrons start falling, right? They're going from a high potential to low potential, and so these electrons are going to start shoving against the other electrons that are in there. And by shoving them, the first electron that comes out of the light switch, if you will, shoves against those electrons, and that one doesn't really move very fast. Its velocity is actually really slow, but the one at the end is going to activate the light bulb almost immediately. Okay, and it's all because of this idea of our electric fields. All right, so what really goes on in there is kind of exactly what we saw with those marbles. Okay, you can imagine here, this is our electron, and this is just an imaginary path that this electron would take inside of our wire. So we would say, like, well, this is our wire like this, and so this is our electron here going, and at each of these points where it changes position, this is a collision point. So it either hit another, like a proton, neutron, electron, it doesn't really matter, it just hit something and it made it change direction. So here's another collision point here, collision, right? And so what ended up happening is these electrons here are going to hit other things, and because of that, they're not going to be able to just travel in a straight line. Now, what we call this overall from here to here, we call this drifting. Okay, so this is the drift velocity, because eventually over time he's going to get shoved down the line, but for now he's pretty much stuck going really slow. So if you calculate the drift velocity for electrons in a copper wire that's at 10 amps, it's only about 0.0000246 meters per second. So these guys move super slow. So essentially what occurs is these electrons are traveling really slow, but the electron field, because each time it hits one of these, it's hitting an electron, which is hitting another electron all the way down the line, just like those marbles we just talked about. And so this electric field moves nearly the speed of light. And so it happens pretty much instantaneously. So it's not the electrons themselves that are going from one point to another at the speed of light. It's the electric field that's created by these charges. All right, and so that's it for current. That's really all we're going to focus on for now. Next time we talk about current, we'll be alternating and direct current, which will be next video. Anyway, so do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.